Hi Kidlets, this is your next set of notes on tides. This will be pretty darn short, so I do expect you guys all to actually watch this and take good notes on it. So tides are a direct consequence of the phases of the moon that we have, and they're due to the gravitational force that is exerted on the Earth by the moon, and a lesser extent to the sun, as we'll see in a second. So this actually happens to rocks as well. However, water, which has a lower mass and lower gravity than the rock that's on Earth, is pulled easier than the rock is. However, there have been a lot of studies that have shown that there is a much higher degree of earthquakes that occur and also volcanic eruptions when we have our highest tides. So our different types of tides are spring tides, our neap tides, and this is a consequence of us having tidal locking. Remember that if we didn't have the moon, we would have a wild axial tilt. Not having a tide and not having a moon would cause our axis to wobble wildly. So tidal locking, or being tidally locked, gravitationally locked to the moon's rotation, stabilizes our orbit. And so the tides, being that the water is the Earth is 75% water. I'm sorry, it's 10 o'clock at night, I'm tired. Being that the Earth is 75% water, this motion of the water around the Earth stabilizes us. So spring tides, as we'll see, occur at both our new and our full moon, whereas our neap tides occur at both quarter moon phases. So the moon is tidally locked to us. So you can think about this really similarly as synchronous rotation. So it is locked, meaning we see the same side all the time. Synchronous rotation means that the rotation is equal to the revolution. And we have tidal effects on the moon as well. So remember that we have slowed it. It is also slowing us. But we also exert this force on the moon's rocky interior. So if this is the core, you can see that here is really the center of the moon. We have offset the core of the moon. Also, if the Earth is over here, I'm just going to draw an Earth. You can see from this yellow circle right here, this is representative of probably where the crust mantle boundary is. So if this be the close side to us, you can see that because we have gravitationally pulled the interior of the moon towards us, we've greatly thinned this near side. So you can see the crust is much thicker on the far side, the crust is much thinner on the near side. So one consequence of that is that you probably have a lot more highlands over here, which we've already seen. It's a lot tougher to disturb that mantle material because the crust is thicker. And on the near side to us, you have a lot more evidence of Maria. So remember, this is not a consequence of the near side being impacted more than the far side. This is probably a consequence of us gravitationally offsetting the interior of the moon, pulling it towards us, so that the near side is thinner and causing that mantle material to come through and the crust being easier to crack when it's impacted by things. So that is how we have gravitationally distorted the moon. So we can see this here again. We know that the moon does not have a liquid interior. The moon does not have a gravitational field. So it has, unlike us, probably a solid mantle, whereas ours is molten, not quite solid, not quite liquid. It most likely has a semi-solid outer core. If it had a liquid outer core, that would generate a magnetic field. The moon does not have one. Same as Mars, same as Mercury. So the crust is much thinner on the side closer to us. And we know this because when we landed on the moon in the Apollo missions, we embedded seismographs and seismometers within the crust of the Earth. We are able to detect tiny little moonquakes, not to say that the moon has tectonics, but they can detect interior movement within the moon. So there's still some seismic activity caused by this gravitational bulging. So here we can see a picture of each of our tides as they relate to our moon phases. So we can see that our spring tide happens at our full and our new. Now, please don't get confused and think this has anything to do with seasons, because we get each of these tides twice a month. So we get our new moon, which is going to pull the water towards it. We also get, as the water is being pulled, the rock is being pulled too. So essentially you get this gap of water that is left behind the Earth. Because the water is pulled, the rock is pulled less, and it leaves this bulge behind. So here you can see that in a new and a full moon, you get a straight line between the sun, the moon, and the Earth. So the gravitational forces are added up when you have a spring tide. So here they're added. So here you have right angles, whether it be a third quarter or whether it be a first quarter moon. Here, the gravitational forces cancel. Sorry, it's really hard to write with my finger. So here's a spring tide. It's an awesome animation that does not show in this app, so I'll show it to you next class. So here we can see the tides again, and we can see the consequence of the moon phases. So here we can see our new moon, and surrounding that would be our crescents here and here. So here we can see we have a spring tide right around our new moon. We can have a spring tide right around our full moon. Then we have our neap tides at our quarter moons. So again, this has the stars, so you do not need to write this. But the moon is our greatest factor in determining the tides. So they're the product of the gravitational forces between the sun and the moon. The moon is closer to us, so even though it is significantly smaller than the sun, because it is closer, it has a stronger gravitational force. Now, if you're interested in the math, in this case, the R means the distance. So this is pretty simple math. So you have your mass divided by your distance cubed, and you can see that the moon's gravitational force is bigger than the sun's. So the moon has about 2 times the effect of the sun. So I may ask you which is greater. I may ask you how much more, but you don't need to know the numbers. If you're interested in the math, there it is. Simple division problem. So the tides are exerting this drag, which is what's slowing the Earth's rotation. So as the Earth is rotating this direction, the tidal bulge is slightly offset. So it should be pulling towards the moon, but because the Earth is rotating in this direction, that bulge is offset. So we get this plane where the bulge is offset, you get this little angle here, and that effect is what is slowing the Earth. So essentially, we will continue to slow until we have also begun to synchronously rotate. So future lunar settlements will see the same side of Earth, just as we see the same side of the moon. I will see you on Wednesday.